Hi everyone. My name's Hollie Moore, and myself and John Hickey are going to present today on the work we've done on the wind-induced vibration response in modular high-rise buildings. So firstly, I'll speak a bit in general about modular construction and then the habitability requirements that are in place for wind-induced vibrations. And then John is going to speak more in detail about our industry partnership on the 10 degrees Croydon project and the wider impact this research has had, and some conclusions as well. So first, a bit about modular construction. So the Ministry for Housing in the UK has set out these 7 category definitions for modern methods of construction. So when we speak about modular construction, we're primarily in category 1, so 3D primary structural systems, and this includes volumetric kind of 3D room size units, which we refer to as modules. So for volumetric modular construction, it's the offsite construction of these room size units. So they're normally finished to quite a high degree in kind of an assembly line in a factory. And then they can be transported to site where they're stacked to, sometimes around a concrete core, like you see there on the right, to form a finished building. It's seen a lot more interest in the last 30 or so years, mainly due to the many advantages. So it can drastically cut construction programs. The modules can be finished to quite a high quality. Studies have shown that there's lower environmental impact. They can be more economical if they're planned correctly. It requires less on-site labour, and therefore there's been less incidents. So traditionally, this form of construction has been employed in more repetitive types of structures, so hospitals or military accommodation. But more recently, it's been employed in residential buildings and in increasingly taller ones as well. So as these buildings become taller, like any tall structure, they become more susceptible to wind-induced vibrations. And with that, then we have uncertainty about their behaviour in the wind. So unlike traditional concrete and steel structures, modular construction hasn't seen the same amount of research. It's newer, it's more novel. And that's meant that we don't have the same level of empirical data. So prior to myself and John's research, there was no previous in situ monitoring of this form of construction. And further to that, then the traditional methods of providing lateral stability, such as outriggers, don't really work in this form of construction. So without empirical data to base kind of calculations or models on, there was questions about what the damping ratio of this form of construction is. And then given the bespoke connections that are typical in modular construction, so intermodule connections between the modules themselves, and then connections back to the concrete core, we kind of didn't know what the modules were contributing to the bending stiffness of the structures. So then that brings up problems when we go to use the equation of motion. As you see there, there's a big question mark over the damping ratio, and then a big question mark over the natural frequency, which is based on the bending stiffness. And without having answers to these questions, it's really difficult to predict the wind-induced vibration response. And then it's really difficult to know if these structures are going to meet habitability requirements. And by habitability requirements, we mean they're normally set out on acceleration limits. So if a building begins to vibrate too much in the wind, that can cause occupant discomfort, stuff like nausea, difficulty concentrating, and dizziness. So obviously no one wants that in their new building, but we need to be able to predict this confidently. So the ISO 10137 sets out the limits for this, and if you look at the figure there on the right, you can see that for residential buildings, the limits are more stringent. So we really need to have confidence in these inherent properties of modular buildings to be able to ensure that our buildings are meeting habitability requirements, and that humans can use them comfortably. So that kind of led to my research for my PhD. So I used a few different techniques. So in situ monitoring, modeling, parametric analysis, and lab testing to try and quantify to some extent the damping ratio, bending stiffness, and mass of these buildings, so that we can better predict the wind-induced response. And this research came about due to an industry partnership between Trinity College Dublin and Bartmani Consulting Engineers. And that was done initially on the 10 degrees Croydon project, which John is going to speak about more now. So I'll stop sharing my screen, and I think John will share his.
Perfect. Thank you, Hollie. Hopefully I'm going to just share my screen here now. And hopefully we can go to full screen. Perfect. Yeah, so thanks, Hollie. As Hollie said, my name is John Hickey, and I'm an assistant professor here at Trinity College in Dublin. And I'm going to speak, I suppose, quite specifically now about work that we did on a project called the 10 Degrees development in Croydon in South London. And 10 degrees, I suppose the key point to take away is that this is a tall modular building, and when it was completed, it became the tallest modular building in the world. It's since been overtaken by a building basically next door. But basically it involved or consists of two connected modular towers like you see in the picture there. And our role in that project at Trinity was we were basically looking at the structural dynamics of this building and how it might move in the wind. And in particular, we were trying to essentially answer the question, will we have a serviceability issue with this building? And will those habitability requirements that Hollie spoke about be met? And typically how we would try to answer that question if we were designing a tall building is we would use the results from some sort of wind tunnel test, which would allow us to establish what the forces induced on the building are by the wind. And then we would use those forces as inputs into the equation of motion that Hollie showed previously. And we would basically solve that equation of motion and try and calculate what we think the peak acceleration would be, and then compare that acceleration to the limiting values. That equation of motion, as Hollie has mentioned on the left-hand side, is two terms that depend or are dependent on the building. They are firstly the natural frequency, marked in orange here, and that depends on the mass and on the stiffness of the structure. In general, people would say that we have a good handle on calculating this, or we were able to calculate this with some confidence from a computer model. On the other hand, the other term in that equation, the damping ratio in red, we would typically, or we're not able to calculate that using a computer model for a structure like a tall building or a bridge. Typically, how we would proceed in a kind of a conventional scenario is we would make a prediction about what the damping ratio is based on previous experience. But in the 10 degrees development, because it was a kind of a very novel structure, we didn't have previous experience. And therefore, we didn't really know what this damping ratio was going to be. And that became important because when we ran these calculations, whether or not we were going to encounter a serviceability issue depended strongly on what this damping ratio was. So I suppose our research question almost evolved into, well, what is the damping ratio in these modular structures? And the way you go about answering that question is you do some in situ monitoring of the completed structure. So basically what happened was the building was constructed, and then we installed a whole series of accelerometers and monitored the accelerations over a number of months. And there were essentially two possible outcomes to that. We could either, I suppose, get lucky and we'd be able to show that there wasn't going to be a serviceability issue, or we could get unlucky and we'd end up showing that there was going to be a serviceability issue. And in that case then, in the latter case, we had come up with or proposed a design for a tuned liquid damper that we were going to install on the top of one of the cores if we managed to show that there was going to be serviceability issues. And then from the monitored data that we acquired, we were able to apply relatively standard operational modal analysis techniques to identify the modal properties. We were able to show that the first natural frequency of that building, of the structure, was about 0.31 hertz. And that was actually slightly higher or slightly different from the value that we predicted using our finite element modeling. And that, I suppose, raised further questions that Hollie has since explored. We were also able to show that the damping ratio of this structure was about 1.1%, slightly over 1%. And that's, I suppose, quite similar to the value that's proposed in Eurocode 1.4 for mixed steel and concrete buildings. And the key outcome, at least for the point of view of the 10 degrees development, was with this combination of natural frequency and damping, we were able to demonstrate that serviceability issues were unlikely. And that was, I suppose, a really good outcome for at least for the developers, because they essentially didn't have to go and pay really for the installation of this extra tuned or auxiliary tuned liquid damper on the roof to mitigate potential issues. So that was, I suppose, quite a good specific outcome of the project. In terms of wider research impact then, I suppose the work gives some insight into the dynamic behavior of modular buildings. But from my viewpoint, I think the main, I suppose, general conclusion that we can come to is that there's no evidence that the damping ratio in modular structures is any greater than in traditional forms of construction, why that's, I suppose, interesting is that it's quite easy to hypothesize or propose that in a modular building, you have all these extra connections and potential sources of movement and frictional energy dissipation that you don't have in a conventional structure. So you can kind of make the argument that the damping should be higher, but our monitoring has shown or hasn't shown any evidence of this. And I suppose essentially that means that the value proposed in the code seems to be quite a good value to use for the design of tall modular buildings in future. And then I suppose, as I mentioned, we also identified challenges in predicting the natural frequency of modular buildings. And Hollie has explored that much more in her PhD, along with carrying out further in situ monitoring at another building that's been built essentially across the road from the 10 degrees development, which is the white building in the picture there, College Road, which is now the tallest modular building in Europe. And I suppose in terms of research into practice, this has been a really nice project because we were able to make a quite specific impact on the design of the 10 degrees development by showing we didn't need this auxiliary damping device. And then, as with any research, we've kind of opened up other cans of worms that we've explored in a more kind of traditional academic way since then. And hopefully, I suppose the aim would be that that work that we've done there will, in time, gradually inform further design practice in the construction of tall modular buildings. So that's pretty much what we have to say. I'd like to thank you for listening. Questions, I suppose we'll try and answer as best we can in the chat. Thank you.